right, this is APAB. We are doing 1.2, which is Intro to Limits. So when I was in 12th grade, Mrs. Brown, my calculus teacher, I always had been really good at math, right? And so I was in calc with Mrs. Brown, and the very first quiz that we had was a limit quiz. And I tanked it. Now my recollection is that I fully failed, and I probably didn't. I probably got like a B or a C and just had never really been bad at math before. But I remember feeling like the stupidest human on the planet because limits were the first thing we did, and I completely tanked and thought, wow, man, I am not smart enough for calculus. So I went to see Mrs. Brown after school, and she sat down with me for like 5 minutes and explained limits to me just one-on-one, and it clicked and it made sense, and then from there on out I was great at calc and everything was fine. Now that's not to say that's exactly the experience you're going to have, but it is to say that limits are a little bit abstract, and that when you first see them, they can feel really confusing, and calc actually gets easier after this limit stuff. So it gets slightly less abstract, I think, in my humble opinion, after we get through the limit section. So if this seems weird and crazy and you hate it, come see me, or if you can't come see me, email me and I'll help you with stuff, and it's fine. So for me, the thing that made it make sense was when Mrs. Brown, way back in 1997, explained to me that a limit is essentially just a y value. Now realistically, it's an output, right? But most of the time, our outputs in math are y values, right? And our inputs are x's or t's. So a limit is fundamentally just a y value that you approach, like that some graph approaches or some equation approaches, or rather expression, not equation, as you approach some input value, right? So if you can try to keep that in your head, that most of the time when you're asked to evaluate a limit, the answer is a y value, right? The answer is going to be a y value, and that's going to make a lot more sense when we start talking about limits graphically in hopefully a couple minutes or maybe in the next video. So let's talk about some notation first. So I don't know why I always write my limits in cursive. You don't have to. It's not like a math thing. I just inexplicably write limit in cursive. You can just write LIM. That's what it is. So LIM, right? So essentially this lim, right, is big, and then this stuff is like a subscript on limit, right? So if you were writing it like a neater person, not someone who clearly failed whatever grade I failed, this x approaches a is small, right? And all of these have this x approaches a. The difference is that this one has a superscript of a negative after the a, this one has a superscript of a positive after the a, and this one doesn't have a superscript at all, right? So what these superscripts tell you is which side you are approaching that x value from. So what this says is the limit of this function, f of x, right? So the output of this function will be my y value, as x approaches a from the left. That negative is the from the left. So this negative tells me from the left. The limit as f of x as x approaches a from the right, that's what that plus sign tells me, okay? This one just says the limit of f of x as x approaches a. So I want the output of this function as x gets close to a. And then the last one I put here is actually not a calc thing. I put f of a, which is just whatever y value the function has when you plug in x equals a. This is not a calc skill. So these three, right, these three are calc skills, right? And this was like an algebra 1 skill, right? Being able to plug in an x value and get something out, okay? So again, you don't have to write limit cursive. I don't know why. For whatever reason, I write limits and natural logs in cursive L's. I've got nothing. I have no logical reason why you don't have to write it inexplicably capitalized. It's just LIM, okay? And it's x approaches a, and then there could be a negative or a positive, right? Superscript there. So again, you're just writing, but the limit is a full-size word, and then this is a subscript, and then in the subscript, there's a little superscript of a negative or a positive, okay? So that's our notation for limit. So let's talk about fundamentally what this actually looks like on a graph, okay? So I'm going to draw you a very simple graph first, and we're going to look just at one spot, and then I'm going to pull up some papers that I have of some slightly harder graphs. So let me explain one other thing quickly. No, we'll do this first. Okay, so here's my graph, 1, 1, 2, 3. Okay, and there's 4. So I'm going to put a dot at 4. Let's have this curve go this way and this way. Okay, so, all right, so this is my y equals f of x, okay? Now, so there's a couple So here's a couple clear points on my curve. Sorry, the computer zonked again. Okay, so this open circle is definitely meant to be the point 1, comma 2. And this closed dot is definitely meant to be the 1, comma 4. This spot right here is definitely meant to be 0, comma 3. I label all of those because I draw terribly, and I don't want you to think that my drawing is the reason that you don't get something. So those are the points that I'm aiming for. Okay, so let's talk about what left and right limits look like. Okay, so if I were to ask you for the limit as x approaches 1 from the left of this function f of x, okay, what that means is here's where x is 1, right? Okay, if I could draw better, but you get the idea. I want to put a little stick figure on the curve just to the left of 1. So what I want to do is I'm going to put a stick figure, and you don't have to draw the stick figure, but just left of whatever point I said. So I said 1, so I'm just going to go just left of 1, and then that guy's going to walk towards that x value of 1. What y value is this guy walking towards? Well, he's walking towards that weird hole that happens at 2. So he's walking towards that y value of 2. Now, if I asked you for the limit as x approaches 1 from the right of that same function, then you would put a guy just to the right. So you'd put that little stick figure guy. And again, I don't actually draw the stick figures. I draw them for you guys. I don't draw them like if I were doing this on my own time. That would be weird. So I put a little stick figure here, right? And I say, okay, he's walking towards where x is 1, right? He's walking on the curve towards where x is 1, and he's also walking towards 2, right? Now, the thing about this double-sided limit, and we haven't talked about that yet, but I'll go over it in more detail, is essentially, if the left limit equals the right limit, that's the answer. Okay, so the double-sided limit, this one that doesn't have a side, not left or right, if the left and right limit are the same, then that's also where the two guys are walking. So essentially, if the two guys are walking to the same spot, then my double-sided limit, the limit as x approaches 1 of this function, would be a 2 because these two are the same, because 2 is the same as 2, so that's the answer. If not, we actually use the abbreviation DNE, which stands for does not exist. And you don't have to write does not exist, you can write DNE. And there is a special situation where there is no left, or there might not be a right, and we'll talk about that in a minute. We'll talk about endpoints. But essentially, if these two numbers are the same, that's also your double-sided limit. But then, and this is the part where I wanted to throw in a little bit of a weird thing on this curve so you'd get the idea. If I asked you the algebra question, if I said, what is f of 1, that would mean what is the y value if you actually plug in the number 1? Well, you can see that if I actually plug in x as 1, there's an open circle here. The closed circle is at 4. The actual value of this function is 4. So the limits don't have to be the same as the actual value of the function. The limit means that these dudes are walking really, really, really close to x equals 1, but they don't actually reach x equals 1. They just walk really, really close. Infinitely close. They can get to like 0.999999999. Like this guy can get to 0.9999999, and this guy can get to 1.0000001, but they don't actually reach 1. What y value are they approaching? Okay? So we're going to do a bunch of practice at this. But before we do that, let's talk about one other spot on here. So I'm going to erase this notation, and if you need to take a sec to copy it in your notes, you can, because it's a video, so you can pause me and go back. So let's look at this same picture, and let's talk about the other point that I labeled, which is 0, 3, okay? So if we were to look at the limit as x approaches 0 from the left of that function, and the limit as x approaches 0 from the right of that function, and the limit as x approaches 0 with no side, right, the double-sided limit, and then actually what is f of 0. So let's look at that point 0, 3, right? If I put a guy, so here's the point where x is 0, I put a guy just to the left of 0 and tell him walk towards where x is 0, he's walking towards a y value of 3. And if I put a guy just to the right of 0 and say, hey, from that right spot, walk towards where x is 0, he's also walking towards a y value of 3. Because the left and right limit are the same, the two guys are going to high five at 3, so that's my double-sided limit. But if you notice, if I actually plugged in, this curve also has a y value of 3. So what I want you to notice about this is that f of x is continuous, right? Which just means in like old school algebra terms, you don't lift your pen, right? You don't lift your pen. at x equals 0, right? So this brings us to where we're actually able to define continuity in a really mathy way. When you learned about continuity in Algebra 2, in all likelihood, maybe in pre-calc, you basically learned that it's a spot on a curve where you can draw it without lifting your pen. And you learned a bunch of discontinuities, right? You learned about some discontinuities. You learned about discontinuities like a vertical asymptote, right? Where this guy goes this way, and then there's this dotted line, and this guy goes this way. You learned about things that are maybe a jump discontinuity, right? Something like this, right? You might have learned about something like a hole, right? That looks like this. Or you might have learned about something that is still a hole, but just like a hole with a lid, which is not a mathy term, but like hole with a lid, right? Which is kind of like the picture I drew there, where you have a hole, but you have some other open circle, okay? These are all discontinuities. The reason that they're discontinuous at these points is because the actual definition of continuity, right? It's the actual definition of continuity, I can spell, at x equals a, is that the limit as you approach a from the left is equal to the limit as you approach a from the right is equal to the double-sided limit is equal to the actual function. So there's the double-sided limit at a, and there's the actual f of a. So the actual definition of continuity is that the left guy and the right guy are walking to the same spot, which means the double-sided limit's the same, and that the actual function has the same value. So here, right here, the left guy, right, this left guy is walking up to infinity, and the right guy's walking down to negative infinity, right? Left guy was walking to infinity, right guy was to negative infinity, so they're not the same. Hey, that's discontinuous, right? Here, the left guy was walking up to this value, the right guy's walking to this value. See how they're not equal, so it's discontinuous. Here, the left and right guy are walking to the same spot, right? And that equals the double-sided limit, but it's not the same as the actual function because there is no value of the function, and the same issue happens here, right, at both of these spots. So the actual definition of continuous is that the left and right and double-sided and actual function are all the same. So the reason that's relevant is that if you see a nice, happy, continuous point, and you're asked about the limits at that point, if a graph has nice, happy, continuous points, you just need to know the y value. So if I gave you a really boring function, like let's say I gave you f of x equals x squared, which is about as boring as nonlinear functions can get, right? And if I asked you about the limit as x approaches 2 from the left, and the limit as x approaches 2 from the right, and the limit as x approaches 2, and the actual value of the function at 2, they're all going to be the same because you see how this is all continuous, right? These are all continuous points. So all I need to know is f of 2, which is just 4, because 2 squared is 4, and know that they are all the same. And you could see that if I had drawn this a little bit better, but here's 2, left guy's walking to 2, right guy's walking to 2, or sorry, to 4. Left guy's walking to 4, my bad. Right guy's walking to 4. Both sides are walking to 4, and then the actual function's value is 4. So that's sort of the gist of how continuity works, right? Most points on most graphs are continuous and super friendly. It's only when we run into these weird things that we're going to have to worry about these limits. In most cases, the limits are just the same value as the actual function themselves because most of our functions are continuous at most places. I really have to go out of my way to construct a function that's going to be discontinuous for you, and that's what I'm about to do. So let's talk about some limits. All right. So, speaking of going out of my way to construct some crazy, crazy limits for you that are going to be difficult, I have a disgusting graph. All right, I think hopefully you can see this. I don't think it's, let's see, I want to put it on the side where you can definitely see it because the light is not an issue, and I think it's a little tiny, but hopefully you'll be okay with it. All right, so rather than write this entire ridiculous graph down, what I did is I printed this graph out. So here's what we're going to find. So this is going to be our example 1 in 1.2, okay? For each a value, you're going to find the following things. The limit as x approaches a from the left of this function. This is my f of x. The limit as x approaches a from the right of this function. The double-sided limit as x approaches a for this function, right? And then the actual function's value at a, okay? So that's what we're going to do for each one of these. So let's go ahead and talk about what the different a values are. So, I'm going to do a is, we're going to do -4. We're going to do a is -3. We're going to do a is -2. We're going to do a is -1. Let's do a is 1. Let's do a is 2. Let's do a is 5. And we'll do a is 6. Okay, so we're going to try, for all of these things, we're going to go ahead and see if we can find those 4 values. So to do that, I'm going to try and draw on this paper, and we're going to see how it goes. So cool. All right, so let's start with a is -4. So here's -4, right? You see how when you look at -4, the left guy and the right guy are walking to the same spot, and so that means the double-sided limit's the same, but also the actual curve is that same spot. Like, there's nothing weird, okay? So this is not weird. The reason it's relevant that there's nothing weird happening at -4 is that, remember, if something's continuous at a point, that means that literally all 4 answers will just be whatever the y value is. So my answer, and I'm going to be kind of lazy and not write the notation down here because honestly I'm a little bit low on space, but the left-sided limit, left guy is walking to a y value of 0, right guy's walking to 0, both sides are walking to 0, and the actual y value is 0. This is a spot where this function is continuous. So I'm going to write CONT for continuous at the bottom, right? Now let's look at x is -3. -3 has some weird stuff, right? So -3 definitely has some weird stuff, right? The left guy and right guy seem to be walking to the same spot, right? At -3, the left and right go walk to the same spot, which means the double-sided limit will also be that same value of y equals 1. But the actual function is not defined at that spot. So what's going to happen is a is going to be a y value of 1 because the left guy's walking to a y value of 1. B, the right guy's walking to a y value of 1, which means that C, the double-sided limit, is also 1. But for D, we're going to write the word undefined. It's not does not exist. It's undefined, meaning the graph is not defined at that moment. There is no output because there is no input at -3, okay? All right, I'm going to switch back to red for -2. So here's -2. What I want you to spot about -2 is that is also not weird. Now, it does have a point, and when we get to further stuff in calculus, we're going to talk about how having a point like that makes something what we call not differentiable, but we're not there yet. So if I'm not picking up my pen, right? See how I didn't pick up my pen at this first red point? Well, I'm not picking up my pen up there, right? If I'm not picking up my pen, this thing is continuous. If it's continuous at x equals -2, then all I have to do is put the same y value for all of my answers, right? So the guy walking from the left up to -2, to an x value of -2 is walking up to a y value of 2. The guy walking from the right is walking to a y value of 2, which means the double-sided limit is 2, and the actual function value is 2, right? Now, if we try this at -1, you get a little bit of weirdness, right? So at x is -1, right, for a is -1, as I approach -1 from the left, I'm approaching a y value of -2, right? So my left is a y value of -2. When I approach from the right of this -1, right, I'm approaching a y value of 3, right? So for A, I'm approaching from the left a y value of -2. My B, from the right, I'm approaching y value of 3. Now what that means for C is that my answer does not exist, because if you need to see y, -2 is not the same as 3, right? And then for D, my value of the actual function is wherever the closed circle is, which in this situation is down at -2, right? So again, not continuous because of that weird jump discontinuity. All right, now let's go back and look at A is 1, right? So here's the x value of 1. Okay, there's 1. You'll notice at this point that I don't lift up my pen, right? It's not weird, right? I didn't have to lift up my pen. Nothing weird is happening. So because I didn't have to lift up my pen, nothing weird is happening. I know that this is a continuous spot. If the function's continuous at a, all 4 of my answers are just the y value of the function at that point. So that y value seems to be a 5, so they're all 5s. And you can see that the left guy and the right guy are both walking to 5. The double-sided limit is therefore 5. All right. The next one we want is where an a is 2. So here's 2. You can see right away that there's a problem at 2, right? There's a jump discontinuity at 2. So the guy to the left of the curve is walking to a y value of 2. The guy on the right of that value on the curve is walking to a y value of 1. So my left-sided limit is that y value of 2. My right-sided limit is that y value of 1. My double-sided limit does not exist, dne, because 2 is not the same as 1. And then the closed dot, the actual function's value is at 1. And when we look at 5 is another spot where if you look at where x is 5, nothing weird is happening there, right? Sorry, alarm on the phone. All right, so if you look here, nothing weird is happening at that y value. That's another spot where we're continuous. So if we have a continuous function, all 5 of my answers are just the y value at that point, and the y value is 0. So let's do one last one, and then we'll end this video. So my last one is at a equals 6. Well, here's 6. The left and right-sided limits are both 1, which means the double-sided limit is also 1. See, that y value is 1. But the actual function's value is up at 3. So what's going to happen is my left-sided guys walking towards a y value of 1. The right-sided guys walking towards a y value of 1, which means the double-sided limit is 1, but the actual function has a value of 3, which means it's not continuous. Okay, so what we'll do next is I'll give you a practice problem to try, and then we'll go from there, all right? So next video we'll start with P1 to match this E1.